So okay, welcome back to the second part of the video on this problem where you have an interval 0 to 1 and two people, person X and person Y, both pick a point from within that interval, and then you want to know what is the expected value of the distance between them. Okay, so our original probability space had the structure of this square where you plotted person X's position on the x-axis and person Y's position on the y-axis, and we know that you could set up two random variables, x, which maps you onto the interval 0 to 1, which gives every point in here the position which x was at, so it gives it its x component, and then we have a random variable y, which ascribes again a real number in the interval 0 to 1, which ascribes to the point of the rectangle its y component, i.e. the position that person Y chose from the interval. Okay, and we know that we can have a joint distribution, x and y, which ascribes points in R2, and specifically it ascribes each point of this square onto a point of this square in R2. Okay. So we could think of making new random variables, however. We could think about making a random variable called big M, which is going to ascribe to every point in here, to every little x, well, to every point in here, it's going to ascribe a number between 0 and 1, and the way it's going to ascribe it is it's going to take it onto the maximum of the two. So it's going to take any little outcome s onto the maximum of x of s, so the maximum of the x component and the y component, okay? And we could also think about making another random variable called, let's call it little l, which is going to ascribe you a real number between 0 and 1, and it's going to ascribe to an outcome s the minimum of of x and s, x of s and y of s. Okay, let's turn over. Right. So, if we want to look at why is this so interesting? Why do we care? Well, because the distance between person x and person y is going to equal m minus l. So it does away with this silly modulus sign. So all we need to do is calculate the expected value of m minus l, and this is going to, by linearity, equal the expected value of the random variable m minus the expected value of the random variable l. So, if we think about these random variables, big M and big L, the way they are going to work is if you think about this square, so this square is here, sorry, then it has points in it, so a little point, let's say little point x and y, and it is going to map it onto whichever one of its components is bigger. So this one is going to be mapped onto its y value because its y value looks bigger than its x value. Okay, so what is the, if we want to know what is the sets, what are the sets that are going to be mapped onto a single value in M? So we've got this function M, which is ascribing you a real number between 0 and 1, and it's ascribing you it based on which of these is your maximum, and it just maps you onto your maximum. So your maximum has to be this. If we want to know what is the inverse image of some element x in here, then we want all the points in here which are mapped onto, let's say, actually, let's give it a symbol k. We want all the points in here which are mapped onto k by this mapping m. Well, that's all points along here. So those are all points. Well, you might think, okay, a good starting point to think is, let's have a look at all the points along the line x is equal to k. So all of these points will be mapped onto k by x. But as soon as you get up here where the y value is getting bigger than k, then of course the maximum will no longer be equal to k. So you need to stop when y is in fact equal to k, and you can draw another line down here because all of these points y is now equal to k, but x is smaller than that. So all along here the y value will be equal to k and the x value will be smaller, so the maximum will be k. Then you've got the point where it is actually kk, and in that case the maximum is still k, and then we go down here where y gets smaller than k and x remains at k, and all of those points are going to be mapped onto k by m. So basically the sets of points that are all mapped onto a single value by m are going to look like these sort of lines here. So if we wanted to calculate the expected value of the random variable m, then we could view it m as mapping. We could view m as being a mapping from, so if we have our abstract probability space, which is the square, we then have our joint random variable x and y, which maps it onto the nice real variables 0, 1 cross, the subset of R2, 0, 1 cross 0, 1, and then we could view m as being a function from here, and then we could apply a two-dimensional lotus and say that the expected value of m is just equal to this function, the integral from negative infinity to infinity of the integral from negative infinity to infinity of whatever this function is, m of little x little y times the PDF, which in this case is actually we should write it the joint PDF because it's going to be 0 on most values of R2 dx dy. However, this is just as complicated, if not more complicated, to do than our original integral. But this is a way in which you could do it. And similarly, for L, there will again be, for the minimum, you can set up another random variable L here, which is going to map you onto the minimum. And in that case, the lines that are going to be mapped onto a single coordinate, instead of looking like these, they will look like, if we have our box here, they all look like things like that, because all of these you'll have a minimum value of, let's say L here. No, let's say K again. So all of these will have a minimum value K because X is equal to K, not this line here. All of these will have a minimum value K because X is equal to K and Y is greater than K. Then you'll get to KK, which still has a minimum value of K, and then you'll go up along X and Y will remain at K, and then the minimum will still be equal to K. So the lines, if you like, of constant constant L value will look like these sort of things here. Okay, whereas the lines of constant big M value look like those. But they are, if you want to calculate E of L again, it will be the integral from negative infinity to infinity, the integral from negative infinity to infinity of L as a function of X and Y of the joint random variable probability density function x and y dx dy. Okay, but as I say, these integrals are no more easy to perform than the modulus of x minus y was. So we won't bother doing this. Instead, what we can do is we can calculate E of m and E of L from the fact that we know what E of x minus y was. So we've done this calculation now. We know it is equal to a third. So let's use it to calculate what E of m and E of L are. So we know that the expected value of the modulus of x minus L was equal to the expected value of m minus L. And we know that this, by linearity, can be split up into the expected value of m minus the expected value of L. We also know that the expected value of m plus L, so the maximum plus the minimum, that is the expected value is equal to, because if you sum up the maximum and the minimum for any point x and y, that's just going to be the sum of x plus y, and by linearity, this is just the expected value of x plus the expected value of y, and we know what the expected value of x and the expected value of y are because it's uniformly distributed, so that's a half, and that's a half, and by linearity here, this is the expected value of m plus the expected value of L. So we get that the expected value of m plus the expected value of L is equal to a half. So what we now have is a system of simultaneous equations. We have the expected value of m minus the expected value of, and I'm going to drop the brackets to make it easier to write, E of L is equal to a third, and then we've got the expected value of m minus the expected value, plus the expected value of L is equal to 1. So add these two together and we get 2 times the expected value of m. So by adding those two together, then when we add these two together, they cancel. We get that this is equal to 4 thirds. Divide by 2, we get that the expected value of the maximum value point is 2 thirds. And we get that the expected value of the little point is equal to 1 minus 2 thirds, which is equal to a third. So that's excellent. So we have calculated the expected value of the maximum of the 2 points which person A and person Y pick. So each of them picks a point. The maximum is whichever one of them picks the bigger point. What's the expected value of that? It's 2/3, and the expected value of the least point, the minimum point, is equal to 1/3.